Hi, I'm Dr. Incognito. In this video, we're going to discuss the direct comparison test. The direct comparison test. Suppose we're given an infinite series which has positive terms. What we're going to do is create another series which also has positive terms, which is in some way similar to the original series. And we're going to make a direct comparison. So we're going to say that either AN is less than BN or AN is greater than BN. If AN is less than BN, or actually less than or equal is good enough for all n, and if the summation of Bn, the series that we created, converges, then the summation of AN converges also. So it's important when we create the series summation of Bn, it's important that we know whether that series converges or diverges. So maybe it'll be a p-series, or maybe it'll be a geometric series. It should be a series whose behavior is known. Then, if that series converges and the series that we're given has smaller terms, then the series that we're given will also converge. So less than a convergent series is convergent. That's half of the direct comparison test. The other half is if the ANs are bigger than the BNs. So if AN is bigger or equal to BN for all n, and if the summation of the BNs diverges, then the summation of the ANs will diverge as well. So greater than a divergent is divergent. And that is the direct comparison test. Before we look at a couple of examples, let's notice that there are two possibilities that the direct comparison test does not cover. If the ANs are greater than or equal to the BNs and the summation of the BNs converges, then there's no conclusion from the direct comparison test. Greater than a convergent, there's no conclusion. If the convergent series adds to 12, then a series that's greater than it might add to 15, thereby converging, or it might add to infinity, thereby diverging. So greater than a convergent will give us no conclusion. And similarly here, less than a divergent series will give us no conclusion. If we have a series whose terms add to infinity, and then we look at a smaller series, they may also add to infinity, but they also may add to a finite number, like 12, and thereby converge. So less than a divergent does not give us any information. So we get information in two of the four possible cases. Less than a convergent gives us convergence, and greater than a divergent gives us divergence. So let's look at an example. Suppose we're considering the summation n equals 1 to infinity of n minus 1 over n cubed plus 4. So the first thing is when we're adding up these fractions, what's going to make a difference here is just the largest powers of n. So n minus 1, when n is very large, the minus 1 becomes insignificant. And similarly on the bottom, when n is very large, the plus 4 is not significant. So these fractions are going to behave basically like n over n cubed, which then simplifies to 1 over n squared. So I'm going to be trying to make a comparison between these fractions, these are my ANs, and I'm going to create another series that's going to be the summation of 1 over n squared. And that's one that we know, it's a p series. So let's make the comparison, which one is bigger. So let's start with the fraction that's given, that's our AN. Now this is less than n over n cubed plus 4, simply because they have the same denominator here, and n minus 1 is less than n. So the smaller numerator makes the smaller fraction. And then this, in turn, is less than n over n cubed, because the fraction with the larger denominator makes the smaller fraction. These fractions have the same numerator, but n cubed plus 4 is larger by 4 than n cubed, and so n over n cubed plus 4 is less than n over n cubed. And this, of course, is exactly equal to now 1 over n squared. Those will be my bn's. So an is going to be less than bn for all values of n. So the summation n equals 1 to infinity of 1 over n squared, this converges. Why? It's a p series. P is equal to 2. And a p series converges whenever p is greater than 1. So 2 is greater than 1, so our p series converges. And now we have a direct comparison. The terms in our series are smaller than the terms in a series which is known to converge. So we're in this situation here. An is less than or equal to bn for all n, where the summation of bn converges. So we can make the conclusion that the summation of an converges as well. So the summation n equals 1 to infinity, n minus 1 over n cubed plus 4 converges by direct comparison. Okay, let's look at another example. Let's take the summation n equals 0 to infinity of 1 plus 3 to the n over 2 to the n. So this example can be shown to diverge by the test for divergence, because the individual terms here are actually going to go to infinity. But let's ignore that for the moment, and let's focus on this example as an example of the comparison test. So the fraction 1 plus 3 to the n over 2 to the n, that's my a sub n, is greater than 3 to the n over 2 to the n, simply because the numerator, 1 plus 3 to the n, is greater than 3 to the n. I've left the denominators alone. And let me just write this as 3 over 2 to the n. So these are going to be my b sub n's. Then the summation of 3 over 2 to the n, and it goes from 0 to infinity, this is a geometric series with ratio r equals 3/2. A geometric series will converge if the absolute value of r is less than 1, and it will diverge if the absolute value of r is greater than or equal to 1. So here the absolute value of r is 3/2, that's greater than or equal to 1, which means the series diverges. So now we're in this part of the comparison test. We're given a series whose terms are larger than the terms in another series, which is known to diverge. So our series must diverge as well. So by direct comparison, the summation of 1 plus 3 to the n over 2 to the n diverges. So again, this one could have been done as an example of the test for divergence. An is equal to 1 plus 3 to the n over 2 to the n. If you take a look at the limit here of an, you will get plus infinity. That's not 0. And so the series diverges by the test for divergence as well. I want to do another example that involves a trig function. Let's look at the summation of cosine squared n over n cubed. In this example, we will use the fact that the cosine of any angle is always between -1 and 1, and therefore cosine squared will be at least 0 and less than or equal to 1. So the fractions that we have in our problem, the a sub n's, cosine squared n over n cubed, they are less than or equal to 1 over n cubed. Leave the denominator alone, and cosine squared is less than or equal to 1. And these will be our bn's. The summation of bn is known to converge. Why? Because it's a p-series. P is equal to 3. That's greater than 1. So our series will converge as well by the direct comparison test. The terms in our series are smaller than the terms in a series which is known to converge. So our series will converge by direct comparison. And let's finish this video by looking at an example where the direct comparison test will fail. Let's consider the summation of n plus 1 over n cubed. If we try direct comparison, n plus 1 over n cubed is greater than n over n cubed, which is 1 over n squared. The summation of 1 over n squared is known to converge, p series p equals 2. But here, our fractions, the fractions that are in our summation, are larger than the fractions in our convergent series. So no conclusion about the convergence here, because we have greater than a convergent series. It turns out this series does converge, but we can't demonstrate that using a direct comparison. There's another test called the limit comparison test, which is a little bit more flexible. We don't require that our fractions be less than 1 over n squared. We simply require that they be approximately equal to 1 over n squared. That's actually good enough. So that would be what's called the limit comparison test. So the direct comparison test is a little bit limited. When we have greater than a convergent, we get no conclusion. Okay, thank you for watching. I hope you found this video helpful.